Alright, so in this video we're going to talk about a concept called LeChatelier's principle. One thing that we haven't talked about in terms of equilibrium yet is can you shift an equilibrium in a particular reaction? All we've done so far is calculate values of K and equilibrium and beginning concentrations and things like that. We haven't seen anything about any way to move your value of K or to shift your position of equilibrium from one side to the other. And actually this is particularly important because there are many industrial processes that are equilibrium themselves. For example, the synthesis of aspirin is an equilibrium process itself, and so to minimize the yield of product, then you want to find a way to shift that equilibrium as far over to the products as you want. If your equilibrium lies over to the reactants, then it doesn't matter how fast it is, you're going to get little product and it's going to be kind of crap, really. So the more you can shift your equilibrium over to the product side, that is better for you if you're working in a company where profit is the big deal. But we're not concerned with that. We are concerned with the basics of what Chateliier's principle deals with. And let's take a particular chemical equilibrium system just like this one. And from what you've seen before, you know you can write out the equilibrium expression for this process here, and it looks simply like this. It's really very simple. You have the equilibrium concentration of NO2 squared from that to there over the equilibrium concentration of your N2O4, and that gives you your value for K. Now whatever that value for K is, one of the things you will have seen already is that this is temperature dependent, so actually changing temperature will affect the value of K. So what LeChatelier's principle talks about is something called a disturbance in the equilibrium. Kind of like a disturbance in the force, but without lightsabers. When a chemical system, this is what LeChatelier's principle says, when a chemical system at equilibrium is disturbed, the system shifts in a way to minimize that disturbance. So you might be asking, well, that's fine, but what does disturbed mean? Disturbed to me means nothing to do with chemistry. The fact is, the term disturbed here can mean several things. There are several ways you can disturb a chemical equilibrium. And one of those ways, we're actually going to look at several different ways. One of those ways is changing the concentration of products or concentration of reactants, because changing both of those will have an effect on the position of the equilibrium. Another way to introduce a disturbance into a system at equilibrium is to change the volume of the reaction or change the pressure of the reaction. Now, from what you've seen before, if you increase the volume of a container, its pressure will go down. Just as if you decrease the volume, its pressure will go up. So these two are inversely proportional. Alright? So whatever you do to one thing, the opposite's going to happen to the other. And we're going to get into the details of each of these here in just a minute. And the last one is simply changing temperature, like we illustrated, like we talked about up above. So the fact is, changing any one of these variables here will affect the concentrations of your products and reactants, which will in turn affect the value of K. All right. So if I was to take this reaction that's at equilibrium, I increase the temperature. What happens is, depending on which way things shift, this gets knocked out of equilibrium because one of these two is increasing or decreasing. And once that happens, the system's going to shift in such a way as to get back to equilibrium and minimize what has just been done. Alright, so let's actually use this guy as an example. Alright, N2O4 going to 2NO2. The fact is that you can actually follow this using the color of the species involved. N2O4 is colorless. It's a colorless gas. And NO2, from I'm sure what you've seen before, is a deep brown color. So if you were to shift the equilibrium towards this, your gas would get more brown. If you were to shift the equilibrium away from here, it would get less brown. Okay? Alright, so let's imagine we're at equilibrium, okay, for this reaction here. Our reaction quotient is exactly the same as our equilibrium constant. So we are at equilibrium here. What would happen if we were to increase? What should we do? Let's increase our concentration of NO2. All right. So what happens is if we increase our concentration of NO2, what's going to happen to this? Well, this is going to increase. If this increases, what's going to happen to our value here? For one thing, we aren't going to have equilibrium anymore, so our value of Q is going to increase. So if we do that, our value of Q gets bigger than our value of K. And so in order to re-establish the equilibrium, that has to shift. Well, which way do you think? Which way do you think it has to shift? If my Q is now bigger than my K, that means this is too high. So I have to shift back this way to the left to regain equilibrium. In this case, that means shifting to the left. And actually, there is a simpler way to follow what's happening here. If you increase the concentration of any species, so if you were to increase the concentration of your products, then the equilibrium would shift away from that, so it would shift towards the reactants. If you increase the concentration of my reactants, exactly the same is going to happen. I'm going to shift away from my reactants, from the side that I increased the concentration of. Okay? So that essentially is the effect of increasing concentration. Decreasing concentration is exactly the opposite. What if I was to say decrease the concentration of N2O4? What if I was to do that? Well, if I do that, my amount of N2O4 suddenly gets less, so this goes down. All right? If this goes down, the equilibrium is going to say, whoa, what's going on? Why is this disappearing? Well, I need to make more of that to make up for what I've lost. All right? And the only way to make more of what has been removed or what I've lost is to shift the equilibrium left to make more. This is exactly the same. If this value goes down, my value for QC is again bigger than KC. So I have to shift left to regain the equilibrium. All right. So, like I said, you increase concentration of something, you shift away from that side. You decrease concentration of something, you shift towards that side. So if I was to decrease concentration of my NO2, which way would the equilibrium shift? Shift to the right, towards the side of what has been removed. All right. So that is the effect of changing concentration. What if we were to look at then the situation here of changing either the volume or the pressure of the system? All right. In order to do that, let's come up with a different equilibrium. Okay, let's talk about the industrial synthesis of ammonia. Nitrogen reacts with hydrogen in an equilibrium process to give ammonia. Of course, the reaction here is balanced, and you always want to make sure that everything is balanced before you do anything else. So what's going to happen if I'm going to change my volume or change my pressure? Well, what's the one state that's going to be most affected by a change in volume or pressure? And when I say state, I mean solid, liquid, or gas. Well, obviously solid's not going to care. Liquid isn't going to care either. It's gases that you have to be concerned about, because it's those gases that are going to dictate what happens. So what you want to look for is when you have a situation or a question that asks you what happens when you change the volume or pressure, look for the number of moles of gas on each side of the equation. Number of moles of gas. So here I've got 2 moles of gas on the product side. I've got 3 moles of hydrogen, 1 mole of nitrogen, both are gases, so I've got 4 moles of gas here. So 4 moles of gas, 2 moles of gas. Alright? So that means my reactants have more moles of gas than my products do. Alright, so let's just do an example. What if I say I'm going to increase the pressure of my system, and I could say the same thing if I was going to say I was going to decrease the volume. If I increase the pressure, well, what does that do to my gas molecules? If I increase the pressure, then I push them closer together. Alright, now my molecules don't like to be pushed closer together, so what's going to happen is the equilibrium is going to shift to the side that makes the molecules less close. So what do you think that means? Which side would the equilibrium shift if I increase my pressure? Alright, well, the general rule is you shift towards the side that has the least number of moles of gas. Alright, shift towards the smallest number of gas molecules. Alright. It doesn't matter how much solid or liquid you have there, they don't count. It's the gas molecules that count. Alright. You could have actually, I could have just said moles here as well. So in this case the equilibrium would shift to the right. Alright. To the product side. What if I was to increase my volume? Well, remember we said before that volume and pressure are inversely proportional. If I increase my volume, then that means my molecules have more room to spread around. If they have more room to spread around, the equilibrium is going to shift to the side that gives me more moles of gas. So in that case, we're going to see the opposite to what we saw up above. In this case, we see a shift towards the largest number of gas moles or gas molecules. Alright? Simple as that. So for volume or pressure, you just have to remember or be able to figure out how many moles of gas, only of gas, that you have on each side of the equilibrium. Alright? Alright, now let's look at the effect of temperature. Alright, and I'm just going to use something generic for this. Let's say we have reaction A plus B goes to C plus D. Alright? And I'm actually going to write it out twice, and we'll see why here in just a minute. If you are looking to figure out what happens when you have a temperature change in terms of the position of your equilibrium, there's one thing and only one thing that you need to know. The number of moles of gas here is completely irrelevant. The only thing that you have to know is, where is the heat in my equation? The heat's either going to be on the product side or on the reactant side, and for that you've got to know one thing. Is my reaction exothermic or endothermic? Alright, if heat is given out on the product side, what does that tell you? Well, heat is given out. Heat is out as in outer, so exo means out. This is an exothermic reaction. If the heat is on the product side for an exothermic reaction, then it stands to reason that the heat would be on the reactant side for an endothermic reaction. Alright? And that's basically all you need to know. So let's just say, if I was to increase my temperature of this reaction number 1. Alright? Well, if you're increasing temperature, you're adding heat across the whole reaction. And remember what we said before about what LeChatelier's principle says, you add that disturbance in and the equilibrium shifts away from it. Well, if you increase your temperature, you add more heat into the reaction, the equilibrium is going to shift away from the side that already has most heat. So you increase the temperature to an exothermic reaction, the equilibrium shifts to the reactants, to the left. Alright? because there is no heat on the left hand side. If on the other hand I increase the temperature in reaction number 2, and I do exactly the same thing, once again I apply my heat across the whole reaction. I'm not applying anything over one side or this side. I apply whatever heat or pressure or volume or concentration across the whole reaction. And so I'm going to shift away from the side that has the most heat. So in this case it shifts to the products. Alright. Now what about decreasing temperature? Well, as you would imagine, it's exactly the opposite as for increasing. So when we said you increase the temperature for an exothermic reaction and the equilibrium shift to the left. If you decrease the reaction, if you decrease the temperature, then the equilibrium shifts to the side that has more heat on it, and exactly the opposite to what we just saw. So just make sure you understand that increasing and decreasing temperatures have exactly the opposite effects for exothermic reactions, and then have opposite effects for endothermic reactions. All right. Okay, let's just do one overall example before I finish. I'm going to write out one more equilibrium here. I'm going to introduce a couple of things. There is an equilibrium that exists between calcium carbonate and calcium oxide and CO2. And I'm going to ask you, what is the effect of making the following changes? Alright, and I'm just going to say that. Okay, so the first one. What's going to happen to the position of my equilibrium if I increase the temperature of this reaction? Well, if I increase the temperature, I have to know if this is exothermic or endothermic. The positive delta H, of course, means it's endothermic, so therefore the heat is on the reactant side. If I increase my temperature, then in that case I'm going to shift away from the heat. I'm going to shift towards the products. Alright, let's talk about our second disturbance. What if we increase our concentration of CO2? Well, what we saw before was the concentration of something that you increase, you shift away from it when you do that. So the CO2 is on the product side. I add more CO2 in, and the equilibrium says, well, yeah, I've got too much now, I've got to get rid of some of it. So the equilibrium shifts away from that. The equilibrium then shifts towards the reactants. Okay. All right. We'll do two more. What if I said this? This may stump you a little bit. What if I increase this? What if I increase my concentration of calcium carbonate? Think about that for a minute. Calcium carbonate is a pure solid, has no concentration. I can't increase my concentration, but okay, how about if I reword that then? Because everybody understands that you can't increase concentration of something that has no concentration. What if I add in more calcium carbonate? Well, just what we said before. Calcium carbonate has no concentration. It doesn't factor into the equilibrium expression, so therefore nothing's going to happen. I could lump in lots and lots and lots of this stuff and it would just stare right back at me. Alright, last one. What if I was to decrease the volume of the reaction? What we said before was the only thing you're concerned about is the number of moles of gas in your reaction. So you've got 1 mole of gas here on the product side and 0 moles of gas on the reactant side. If I decrease the volume or increase the pressure, I'm going to shift away from the side that has more moles of gas. Or I'm going to shift towards the side that has less moles of gas. So in this case I'd shift towards the side that has, in this case, no moles of gas. I'd shift towards the reactants. Alright. And so that is essentially a little bit about LeChatelier's principle, how it works, and how an equilibrium overcomes disturbance. Thank you.